Myself Reshmi Barua. Today our topic is about investigation of UPS as a reactive power compensator.
Go to slide number 3. Pass it.
So basically, why we need the power factor correction? Nowadays, what happened? We use various type of power converters like AC DC or DC to DC. We extensively use it, and also these power factors are give a flexible output voltage and have high efficiency. But these converters take the current in the form of pulses from the utility grid, so that the high total distortion and the poor power factor are the major disadvantage of this converter. So as we see that sorry sir as AC to DC converter consisting of line frequency diode bridge rectifier with a large filter capacitor, we use mainly to convert from AC to DC rectifiers, and with that rectifiers we use filter in order to produce a constant DC output. But what is the major disadvantage using this filter is that the input current that we are getting becomes distorted or damaged, and there is a huge amount of harmonic is inserted. So in order to remove that part, instead of filter, we will be using the boost converter. Konkon? Hello? Hello? Yeah, we will be using the boost converter, and with that we will be using the hysteresis control method in order to produce a sinusoidal input waveform without being distorted, and also to reduce the power factor immensely, along with the total harmonic distortions will be reduced. These are the main objectives of our project. Then Konga, next slide. Here is the schematic diagram of our project. We have here two circuits mainly. In the upper part, we see the non-linear loads. That is our load at that is the domestic load or whatever load. We have the non-linear load, and it is being supplied by the AC source. So when the switch is being closed, we have a continuous AC supply. But when the switch is on off, what we see that from the lower part of the picture, the voltage that is 240 volt is being boosted to 400 volt, and then the DC is converted to AC, and it is being supplied to the non-linear load. Again, when the switch is on, the upper part, that is the AC source, supply the current to the linear load, and when it is off, the lower part supplies it. So this is the main objective of our proposed UPS as a reactive power compensator. Over next slide. So, from the beginning, we have at first done the boost converter in Simulink, and then we have done the single phase inverter with RL load, and then finally we have designed and simulate the power factor correction boost converter using the hysteresis control. So next is about the boost converter. Onga? So as we know, the boost converter is used to boost the voltage, that is act as a step up converter. Whatever input voltage you're giving, it will step it up. So let me explain how it works. At first, let's see when the switch is on, that is it is being connected to the upper part, that is 1 minus d where it is written, and we will see the DC load DC voltage source will provide a continuous current through the inductor, and it will flow through the load, that is during the switch on period, and while it is off, that is the switch will connect to the capacitor, and then it will flow through the inductor and it will form a closed loop, and the capacitor will be charging the load at that time. As we can see, the boost converter steps up the DC voltage, and along with it, it will step down the current. So why this process happens? Stepping up of the voltage and stepping down of the current in order to maintain a constant power output. In order to maintain the constant power output. So these are the equations, or these are the formulas related to it. The ideal gain is 1 by 1 minus d, where d is the duty cycle. And then the current ripple formula is d into 1 minus d whole square r into ts. Ts is the switching period of the time. switching time period of the converter. Then the voltage ripple is that dTs by RC. All these formulas are being derived using that voltage second balance equation and the current second balance equations. Next slide, Konkan. So this is the simulated model of the buck boost converter, where the gate pulse is given through a pulse generator, where we can control the duty cycle with that, and the input voltage and the simulation result will be shown in the next slide. Konkan. So we have given 240 voltage and with duty cycle 60%, and we have found the output as 400 volt, and then the input is 240 and the output is shown nearly to 400 volt approximately, and then the current waveform is shown in the next slide. So we will be the input current is nearly 8.5 and the output current is approximately 5.8 with the output current ripple is also there, which is 5% of the input current. Similarly, the voltage ripple is taken as 5% of the output input voltage. The next slide is about the inverter. This will be explained by Konkan.
Thank you, Rishmi. So, single phase inverter with the RL load. In the slide, there is a single phase full pitch inverter. So let's move to the next slide. So this is the simulated diagram which we have simulated in the MATLAB. So there is a RL load in which L represents the inductance and R represents the resistance. There are four switches D1, D2, D3 and D4, and there is a DC source, and there is a capacitance C and resistance R. So when a DC source is connected as shown in the figure, so at first there is a triggering of the D1 and D4, in which that is from the DC source the current is passed from the D1 and from it passes through the D4, and it does complete the cycle, and after that D2 and D3 are triggered, in which the current passes through the D3 and D2, and after that it completes the DC source. So in the simulated graph, we can see that there is a output current and output voltage, in which the current, as we can see, there is the current is some part of the current in the first half cycle. We can see that some part of the current is below zero. From that, we can see that when that part of the graph in which the current is less below zero, we can see that the current is negative and the voltage is positive. So when the current is negative and voltage is positive, there is a diode D1 and D2 is activated, and the current is supplied by the load. As we can see that the load is both resistance and inductance. The inductance supplies the current, and thus the current flows in opposite direction. That's why the current is negative. And for the upper half, as we can see, the voltage is positive and the current is also positive. So current will flow from the supply, from the DC supply. So in the next slide, as we can see, the subsystem of the single phase inverter with the RL load. Here we have used a sine wave and a relational operator so that it can be compared, and after we use the after using not the operator, then we use the signals in the switches D1 and D2, D3, D4, so that it could be triggered properly. So as we can see, the simulation result, the output current and the output voltage. The output current is as the output current, the voltage, the output amplitude, as we can see, there is a 60 and minus 60, and the voltage is between the 100 and minus 100. So this is the simulation result. Next, we can go to the design.
Okay, thank you, Konkan. Now, here with the designing process for power factor correction, boost converter using hysteresis control. As we can see on the left-hand side, the rectifier is being supplied by the AC supply, and then on the right-hand side, we can see the DC to DC PFC converter, and along with it, there is a bulky capacitor. This is mainly used to rectify the pulsating DC voltage from the rectifier, and due to this bulky capacitor, mainly the distortion of the input current is happening, and so does the poor power factor is produced. Now we can say that there are two loops. These two closed loops are mainly used in order is required mainly in order to improve the power factor. So one is the voltage control loop on the right hand side, and on the left hand side we can see the current control loop. So the voltage control loop is taken reference from the output side, so that we are going. So here we are going to control the output voltage mainly. As we can see the voltage reference there. So when we put some finite value in the V reference, and so here we can control the output voltage, and it will try to settle down the output voltage according to the voltage reference. And the inner loop, which is the current control loop, it is used to maintain the inner current in sinusoidal, so that the total harmonic distortion of the line current is maintained according to the requirement. So basically, this is the block diagram of the power factor rectifier. On the figure B, which is the line diagram of the hysteresis control, we see that the current from the inductor side is being fed and is compared with the with a reference current, and it is fed to the hysteresis loop, and and they are being compared, and putting the hysteresis loop there, so that it can be switched, so that it can switch the line current according to the graph. So we can switch here we can switch the inductor current by upper band and the lower band values, which we are going to put in this which we are going to put in the block, that is the in the gate pulse of the MOSFET. So in the next slide, so this is mainly the hysteresis control scheme. So in this hysteresis control method, it has a constant on time and the off time. This is the advantage of hysteresis control method. And also it controls only one. It takes only one current command. That is, it used to limit either the maximum input current or the minimum input current. The hysteresis comparator are used to impose the hysteresis band around the reference current. One of the most important advantage is due to its simplicity, and it acts very quickly. So we can see mainly the reference value and also the upper band and lower band. So how it works is that when the inductor current goes at the point of crossing the lower band, the voltage is triggered on. And again, when this inductor current will cross the upper band, the voltage it will turn off the switch, and we can see the voltage is turned off at that particular point. And this is how it mainly controls the harmonic, as well as it improves the power factor. In the next slide, we will be seeing the traditional rectifier without any control method. So overall, we can see here the boost converter which is being supplied by the AC voltage, and we can see in the lower part of the figure the power factor measurement, a measurement circuit, and we can see the power factor is very low here. And in the next slide we will be seeing the output voltage, and the output here on the left hand side is the output voltage, and along the right hand side is the input current. So from this figure we can see that in the output voltage, in the initial beginning there is a peak in the output voltage. So this peak basically comes from the bulky capacitor that we use. This peak is due to because the bulky capacitor acts as a short circuit, and due to which the output will go very high with the rated voltage. And it is seen that this peak is almost 1.5 times the rated voltage. And also we can see the ripple in there. Though this output voltage gives a DC voltage as it is seen, but the main factor is with the input current. In the input current on the right hand side, we can see a very high distortion, very high distortion. And also in the initial part, due to the short circuit of the bulky capacitor, we can see a very high exceed in the current in the initial part. And then on the later part, we can see though it gives a pulsating type of input current with a high distortion as shown in the figure. And in the next slide, we will see the FFT analysis. Here, the FFT analysis is done in order to see the harmonic distortion of the input current. As we can see, the total harmonic distortion is 16.32%, which is much more higher than required. Actually, much more higher than the standard set by the Indian government. As we can see, for above 60 kV, according to the Indian standard, 60 kV above voltage should have it should have around the distortion, that is 60 kV and below. It should have a total voltage distortion, that is the harmonic distortion, around 5%, and it can be seen that it is around 60.32% with around 240 voltage. And on the next slide we can see the boost converter block diagram. We can see the boost converter with the hysteresis control method. Here the hysteresis control loop is used, where the voltage reference is taken as 400 volt from the for the output, and along with it we can see the hysteresis band named as relay 1. So this band is used to control the input current, as we have seen in the previous slides, and this gives the gate plus a pulse to the MOSFET as shown in the boost converter. And we can see the power factor is nearly 0.9942, which is nearly as desired, that is nearly to 1. And on the next slide we will be seeing this power factor circuit. Here we have taken the voltage, input voltage and input current, and from which we will get the power factor by comparing it to 0.9942, which is nearly to 1. And on the next slide we will see the simulation result. So this is the output voltage. From the output voltage, that is on the left hand side, we can see the peak is almost removed, and the ripple is also very less as compared to the other circuit where no hysteresis control or any control method has been used. And on the right hand side we can see the input current, which is nearly sinusoidal. In the previous slide without the control, we can see there were lots of distortion. Also the initial values of the current were very much high, but here all this has been removed with the control circuit. And on the next slide we will see the FFT analysis. As we can see, with the FFT analysis, the harmonic distortion is almost nearly 0%. That is, all the harmonics has been removed with the use of the controller, and so the power factor we were getting was nearly 0.992%, is nearly to 1. And on the next slide we will see the comparative result of both the performance of the boost converter with and without hysteresis control. We can see that in the first part we will see that the boost converter without the hysteresis control method, the total harmonic distortion was 60.32% along with a power factor which was very much low, that is 0.000736. And with hysteresis control, we can see how much difference the result has shown. The total harmonic distortion is completely 0.00% and along the power factor is 0.9942. So this is the improvement with the use of hysteresis control, where the harmonic distortion is removed and along with it the power factor has been improved immensely. And on the next slide we will see we have the conclusion here. As we have seen, the work we have done has addressed the problem of reducing the total harmonic distortion. Along with it, it has improved the power quality drastically. And with this, the simulation result shows the hysteresis control offers power factor very close to unity, and the supply current THD is also nearly 0.000%. So here the conclusion is, with the hysteresis controller, without the hysteresis controller, the power factor and the total harmonic distortion, which is very much, and with the hysteresis control, we can immensely see the difference, which is nearly 1, where the power factor is nearly 1 and the harmonic distortion is 0.00%. And our scope for future work, which is shown in the next slide, is that the boost power factor correction converter with hysteresis control, which is done in offline simulation. We will be analyzing it in the real-time simulator, and also we will be designing we will be implementing the hardware in the future work. And on the next slide is this the reference, where we have taken reference from 3 different sites. The first is the journal naming a single phase UPS system with harmonic suspension and reactive power compensator in the month of September 2009. And in the second is the design and simulation of boost converter for power factor correction and THD, published in 2014. And on the third number is we have taken the reference from a thesis, simulation of active power factor correction using boost step converter, published in October 2014. So
Hello, no need to explain this.
okay, sir.
Okay.
So we immensely want to thank our supervisor Manojit sir, and also our friend and head of the department, Dambur sir, for giving us such an opportunity.
What is the switching frequency of your control
Sir,
switch?
yes, sir. The switching frequency is around 4 into 10⁻⁵ seconds. Actually, frequency is 25 kilohertz. So inverse of that is a switching frequency, that is around 0.04 millisecond.
I was asking about switching frequency.
Yes, 75 kilohertz.
Okay. Which switch you are using there?
Yes, sir.
You are using which switch?
Yes.
There is a complementary switch or not in your boost
Yes, sir.
converter?
Yes, sir.
Okay. So which one? Which 3 consist of complementary switch?
Oh, which pardon, can you repeat it once again?
Complementary switch is there or not?
Sure. Yes, sir.
Are you familiar with? There is a complementary switch in
Some MOSFETs.
So which 3 are consisting of complementary switch?
Complementary.
So MOSFET is used as the complementary switch.
MOSFET and
MOSFET IGBT.
MOSFET तो एक हो गया, तुमने कितना स्विच यूज किया यहाँ?
इधर हम लोग ने एक ही स्विच यूज किया है.
अच्छा, तो एक स्विच यूज किया और एक डायोड भी यूज किया ना?
हाँ सर.
Yes, sir.
और एक इंडक्टर, ये तीनों को मिलके कॉम्प्लीमेंट्री स्विच बोला जाता है.
Yes, sir. Yes, sir.
तो मेरा क्वेश्चन है कि तुम्हारा जो दो स्विच है, एक कंट्रोल स्विच diode control switch है on control switch है. So in your control switch, which switch you are use?
So MOSFET. It can be triggered by the pulse generator. It has been triggered.
You are using MOSFET here. So can you replace this diode into a control switch?
No, sir.
No, sir.
Sure.
Yes, sir.
We can, but it will be converted to different converter.
Okay. Okay, you just check it. Okay.
Yes, sir.
Shall I replace this diode into a control switch or not? And what is the inductor current in terms of output current?
Inductor current.
Show
Oh,
me the graph.
sorry.
You are showing the graph of inductor current, na?
Yes, sir.
Go to the result. Showing inductor current, and diode current, switch current. Yeah. Go to the result part.
Sir,
Slide. Go to the result part. Konkan.
Yes, sir.
Go to the result part.
One sir.
Next. Next. Next.
Hello, sir. You want me to go to the end part?
नेक्स्ट एक इंडक्टर करंट दिखा रहे थे ना, इंक्रीजिंग एक्सपोनेंशियल इंक्रीजिंग डिक्रीजिंग करंट दिखा रहा था, वो वाला तुम लोग स्लाइड मेंशन नहीं किया, कैसे बताऊं मैं?
That is of inverter actually. Go to the output. Yes, yes, yes. Not this.
This is the output.
inverter current. Konkan inverter current. Single phase RL inverter.
Okay, let it. Rasmi, you told me what is the value of average current of inductor current in terms of output current. Say output current is I naught. Okay.
Yes, sir.
Okay. What is the value of inductor current?
Sir, pardon?
How to calculate the inductor current in terms of output current?
Yeah, inductor current in terms of output current, sir.
Output current, in boost converter.
So inductor current is 8.75 ampere. And
I was just asking how to calculate it.
oh, sir, how to calculate it? Inductor current is equal to output current by 1 minus D.
Okay. ये कैसे मिला?
Sir, from this one.
डेरिवेशन करके मिलेगा ना? वो डेरिवेशन
sir.
में क्या तुमने लिया? Okay. हाँ, back हाँ, okay, ये stop here. Next. Next. हाँ, stop here. यहाँ पे तूने एक डेरिवेशन करके मिला होगा ना?
हाँ, yes, sir, yes, sir.
Divided by 1
Yes, sir.
minus 2. तो वो डेरिवेशन
Yes.
में क्या कंडीशन लिया था कि शुरू से क्या कंडीशन लिया ताकि ये डेरिवेशन हो पाया?
That is the power is constant and that is voltage second balance equation. That voltage second balance equation. From the voltage second and input current balance equation.
V output is equal to V source plus V in the voltage of the inductor. From that we can get V source which is 240 volt plus V and the voltage of the inductor.
Divided by 1 minus 2. From voltage second balance equation.
No, sir. The current second balance equation.
Which current it is?
Sir?
Which
Sir,
current?
Sir, output current. Output.
Output
That is-
current.
Sorry, sir, input current. I not equal.
अरे बैलेंस मतलब क्या है? you are equaling two current, na?
Yes, sir.
Switching on or switching off. That is,
Switching.
you are balancing,
Yes,
na?
sir. Yes, sir.
Whose current you are balancing?
This one, sir. The inductor current, source current.
ये capacitor current.
No, sir, not capacitor.
One second, 1 second. So that is the, yes, a capacitor current.
Okay. You see, it is capacitor current because average current of capacitor current equal to 0. Okay, you see. Okay. Anyone can ask. Meeting will be ended
Okay,
in.
Kankan. Hello.
Yes, sir. Yes, sir.
Kankan, tell me what are the disadvantages of power factor? If you have low power factor, then what will be the problem?
So if we have the low power factor, then there will be a more reactive power capacitor. As we know that power factor close to 1 has the has low amount of losses.
What?
Then there will be less amount of the total harmonic distortion in the current waveforms. And
No, I am asking, not asking about this TSG thing. I am asking that if you have low power factor, then what will be the problems at your, if you, let's say your incoming supply at your home, if
Yes,
that power factor is very low, then what will happen to your home appliances?
there will be the more losses in the device in the instrument.
Losses in terms of what?
The resistive losses, the heating loss.
How those things will happen?
So power factor from the definition we can get that
Rasmi, you tell.
Yes, sir.
You tell it.
Okay. Sir, due to low power factor, there will the efficiency of the maximum equipments get lessen, and also there will be excessive amount of heat loss due to the less power factor. Because so also 1 second.
Look, this is the first and foremost question to be answered before starting this project, right? Why we are improving power factor? At our home side, it is for home application, na? So why it is required to rectify the power factor? Anna?
Yes, sir. So in order
That
to
thing should
means,
be clear. Yeah.
yes, sir. So heating losses in the conductors and also in the electric heat loss is due to the electric in the resistances in conductors.
Okay. Okay, Kankam,
Yes, sir.
other than saying you both together did this project, you tell me how much percentage of contribution you have in this project. What are the things you have
50%.
contributed? 50%. No, what are the things you have contributed? What are the things you have simulated?
The push converter, RL inverter.
These things you have simulated. And
Yes,
Rasmi,
sir.
what you did?
Sir, almost all I have did means boost converter also, RL inverter also, and the other part that is the power traditional boost rectifier without the hysteresis control and also with the hysteresis control
Okay.
and
So
all
what
that.
are the values? Hey, Rasmi, what are the values you have provided in that L and C of boost converter? What are the
Yes,
inductor value? How did you
yes, sir.
calculate those?
Sir, inductor value I have given 9.21 millihenry along with capacitance value is 0.457.
I'm asking how those formulas actually derived. Because
As
for
we can,
capacitor, let's talk about capacitor. To calculate any value of capacitance, how much capacitor you required. For that
yes, sir.
purpose, how you will calculate what are the things are required to calculate a capacitance value?
In a given circuit, as we know, uh, we shall know about the that Kirchhoff's voltage law by applying Kirchhoff's voltage law, different values
Not
of
Kirchhoff's
capacitance.
voltage law here, not Kirchhoff's. For a capacitance value to capacitor, what capacitor actually does? What is the primary work of capacitor?
So it can be used to filter the AC circuits. Filter. Yeah.
What kind of filter it do?
So capacitor does not allow the DC to pass through it, and it only allows the
DC to pass
AC.
through.
Yes, sir. Does not allow.
Where did you study all these things? Rasmi? Rasmi? Oh, RRB madam.
Sir, hello.
हाँ बोलो. Did you listen my question? Rasmi?
Sir, yes, sir.
Did you listen my question or?
Yes, sir. About the means how the capacitance and inductance have been calculated.
Yes.
Yes, sir. Yes, sir. I will show it to you. Means I have already done using the voltage control second balance and the current control second balance. I have derived it already.
No, I'm asking.
Actually, sir, means in one complete cycle, that is in one complete cycle, we are calculating the voltage. That is during the switching on time and during the switching off time. That is voltage second balance refer mainly to the total voltage second applied to the inductor during the switching cycle, and that
Oh,
must be
Krishmi,
zero.
you are just diverting from the topic. You just shift that slide.
Okay, sir.
In this slide, that is asking that how you have calculated the values of inductor and capacitor. Okay, so you are
Inductor.
telling
Oh,
me.
sir. Okay.
Wait. So
Okay,
you
sir.
are telling all those voltage second and current second balance. But why
Oh,
you are
sure,
doing
sure.
that voltage second balance and current second balance? What is the source? That's very tough.
Oh, why we are means using the voltage second balance? Hello.
Okay,
Yes,
Rasmi.
yes. That is the question. That why you are
Okay,
using
sir.
that voltage second balance and current second balance?
So in actually in order to calculate the duty cycle from that, and also
No,
the
oh,
कहाँ चली जा
no,
रही है?
no, no. You have written those answers in the slide only. What
Yes, sir.
what will be your answer that is written in the slide only?
So actually to find the capacitor, inductor, and also the current ripple, voltage ripple, and all, and the gain.
Fitting ना?
Yes, sir.
That value is ripple. From that ripple, you actually go to that energy balance equations, and from that energy balance equations, you find out the value of inductor. If it is a current fluctuation, then you have to put a inductor, certain amount of inductor. That value can be calculated
Yes,
from
sir.
that current ripple. है ना?
Yes,
From
sir.
voltage ripple, you will calculate the capacitor. That is the
Yes,
simple
sir.
concept behind it.
Yes, sir. Yes, sir.
इसका मतलब ये नहीं कि ये देख खाली बूस्ट कन्वर्टर का बात नहीं, तो कहीं भी किसी भी सर्किट में कहीं भी यूज करेगा, तुझे अगर कैपेसिटर इंडक्टर का वैल्यू फाइंड आउट करना है, तो यू हैव टू फाइंड आउट द वैल्यू ऑफ रिपल्स. करंट वैल्यू कहाँ से मिनिमम कहाँ जा रहा है और मैक्सिमम कहाँ जा रहा है, कहाँ से कौन से बैंड विड्थ के अंदर वो फंक्शन कर रहा है, वो बैंड विड्थ पता चल गया, देन यू विल गो फॉर द एनर्जी बैलेंस इक्वेशन एंड यू विल फाइंड आउट द इंडक्टर वैल्यू. है ना? ये बेसिक कॉन्सेप्ट है इसका. समझी?
Yes, sir.
So what are the ripples that you have considered to calculate the value?
So for current
Like
and
5%
voltage, we have
of
considered
the
5%.
input.
And for
Input
voltage?
Voltage also 5% of the output of the input voltage.
You see,
Sorry,
you have
output voltage.
calculated those values from there, but you have skipped that term.